our next tutorial for organic chemistry, which is Introduction to Acid and Base. Without further ado, let's begin our tutorial session, and please pay attention to this tutorial because there is going to be a quiz at the end of the video. An alkeneous acid is a molecule that when dissolved in water will donate a H plus in solution, simply put, a proton donor. The trick to recognizing an alkeneous acid is to look for a molecule that starts with a hydrogen and typically contains an oxygen or halogen. Common examples of alkeneous acid includes hydrochloric acid, HCl. An alkeneous base is a molecule that when dissolved in water will break down to yield an OH negative or hydroxide in solution. To recognize the alkeneous base, look for a molecule ending in OH but not following CHX, which refers to an alcohol. Alkeneous base examples include sodium hydroxide, NaOH. Constant acid, like an alkeneous acid, is a compound that breaks down to give a H plus in solution, or simply put it as a proton donor. The only difference is that the solution does not have to be water. We can still refer to the exact same acid as listed for the alkeneous acid example, but this time we'll change the solvent to ammonia, alcohol, or anything else. For example, ammonium chloride. This is where we start to see the difference between the Bronsted-Lowry and Arrhenius definitions. While the Arrhenius base referred to specifically to the hydroxide OH ion, the Bronsted-Lowry base refers to any atom or ion capable of accepting or bonding to a free proton in solution, for example, ammonia, NH3. The Lewis definition for acids and bases is the most extreme because it's not dealing with protons specifically. Instead, the Lewis definition deals with the movement of electrons. Think of Lewis as electrons. A Lewis acid refers to an atom or molecules that accepts an electron pair. Think back of your pushing arrows for orgomechanisms. Every time you draw an arrow representing the movement of electrons, the atom getting attacked or accepting those electrons is the Lewis acid in that reaction. Common Lewis acid example in organic chemistry is aluminium chloride. Since the Lewis definition has to do with the transfer of electrons, you can guess by now that a Lewis base is an electron pair donor. Once again, think back of your reaction mechanisms. The molecule using its electrons to attack another atom is an electron pair donor and a Lewis base. A common Lewis base example is chloride ions, Cl negative. Now we are going to look at a general acid-base reaction. So if I give you a HA and B, how we know which one is acid and which one is base? Well, let's see. An acid would break up to give me H plus, a base would be OH minus. So HA is an acid and B is a base. In this reaction, HA donates proton to B. A negative, a conjugate base, and HB, a conjugate acid, are formed. Acid dissociation constant, Ka, is equal to proton or H plus concentration, A minus, which is the conjugate base divided by the concentration of the initial acid or HA. Then we come to see for the pKa value, which is equal to negative log of Ka. Next, we know that Ka is directly proportional to H plus ions. So for strong acid, if we increase the concentration of H plus ion, then Ka will be increased, pKa will be decreased. However, for weak acid, decrease the H plus concentration will decrease the Ka, and so pKa will be increased. Alright guys, now we have done with the definitions and the formulas. Easy, right? Now we go on to how to determine the acidic strength by using this mnemonic, which is CARIO, C-A-R-I-O. The first C is charge of acid and conjugate base. A is atom holding charge. R is resonance effect. I is inductive effect. And last but not least, O is orbital hybridization. While learning for acid strength, you tend to think the terms of hydrogen. Hydrogen atom falls off or the hydrogen atom breaks off, but it's really about atom holding that hydrogen atom and what happened to that atom when the hydrogen is gone. When comparing acid molecules and looking at the atom and holding the acidic hydrogen, we are looking for two different trends. When the atom earn the same period, you're looking at electronegativity. And when the atoms are in the same group, you look at the size. For example, let's say you are asked to rank the following molecules from low to high or order of increasing acidity, which is fluorine and bromine. Fluorine has the smaller size compared to bromine, and this makes fluorine as a less stable conjugate base, which means less acidic, while bromine, the size is bigger than fluorine, will make a more stable conjugate base, which is be more acidic. Next, we will be looking at ethanol and ethanoic acid or acetic acid, and they pretty much the same structure. Both have a two carbon chain, and even in OH, the only difference is the acetic acid has a carbonyl or double bond oxygen. Both of the conjugate bases have a -1 charge, so the same charge and then oxygen holding the charge, so at the same atom. The difference is etoxide or the conjugate base of ethanol has an oxygen sitting by itself, and then oxygen is the only atom capable of holding that charge. So ethanol can only form one Lewis structure. Etoxide does not have resonance. It carries the charge by itself, so it's less stable, and if it's less stable, it comes from the weaker acid. The negative oxygen of the acetate will use one of its electron pairs to move towards the carbonyl atom, creating a pi bond between itself and that carbonyl. But carbonyl have 5 bonds, which is not allowed, so one of the bonds between carbon and the black oxygen will break and collapse as a lone pair onto the oxygen atom. Two resonance structures are formed. So in this case, it's more stable, and that means it comes from a stronger acid. The more the resonance structure, the higher the charge distribution, the higher the acidity. Now we are done with the resonance, and we will move to inductive effect. You will have to think induction as influence. For an acid to form a stable conjugate base, it has to be stable with that negative charge. If you have an electronegative atom very close to where the conjugate negative charge is going to form, that electronegative atom is going to influence the molecule to form a negative charge because it won the negativity. Once we have the negativity, and it's almost as it pulls on negative electrons towards itself, making the atoms holding the charge carry less burden. This is different than resonance, where there is actual sharing of electron instead. It is more than an influence to calm down the molecule. For example, 2,2,2-trifluoroethanol has an inductive effect because CF3 withdraws electrons density, and will stabilize the conjugate base compared to ethanol that have no additional electronegative atoms. Therefore, 2,2,2-trifluoroethanol is more acidic than ethanol. Okay guys, hold on with me for one more second because we will go to the final effect, which is the hybridization effect. Now, if we look at the mind map, for the first one, because we have no pi bond, that is sp3 hybridized. The second one has one pi bond, making it sp2 hybridized, and the third has two pi bond, making it sp hybridized. We are looking at sp3 versus sp2 and then sp. These hybridized orbitals are formed by combining a different number of s and p. We have to remember that the s orbital sits much closer to the positive nucleus, So if I take an acid, pull away hydrogen and give it negative electron to form a conjugate base. The closer I put those negative electrons to the positive nucleus, the more stable it is going to be. So the more S character we have in that hybridization, the more acidic molecule it is going to be. S character is simply percent S out of the total number of orbital. The higher percent of S character, the more stable the conjugate base, the higher this acidity strength. Okay guys, that's the end of our video. Thank you guys for watching. I would like to say thanks to my teammate Gobind, Prashad, Puyin, Aimi for the beautiful mind map, and me myself, which is Moon. And about the quiz, there's no quiz. We're just messing around with you. Okay, I hope you give your full focus, and good luck with organic chemistry. Bye.
Let it go, make my body go. Make our bodies high.